Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. So, where are we? Well, this is part 2 of the solution to question number 5. So hopefully you've already watched part 1. And again, it's part of the grade 10 academic summative solutions questions. So part 2 of question 5, let's see where we were. So the question said, determine the type of quadrilateral created by the points of intersections of these 4 lines. So we started by discussing how you identify quadrilaterals. And we said, well, you have to look at sides being parallel. You have to look at for perpendicular sides. So parallel and perpendicular, so we had to look at slopes. We also had to look, were opposite sides the same length? Were all sides the same length? So we also had to look at length. And we had discussed the fact that these were the possible quadrilaterals. And we had already done this part. We had looked for parallel and perpendicular. And we had already discovered that we definitely had a parallelogram because opposite sides were parallel. So cross those ones out. Then we noticed that adjacent sides were not perpendicular. So we looked at the slopes and said, well, we can't therefore have a rectangle and we can't have a square. So we're down to either it's a parallelogram or it's a rhombus. So then we realized that if we want to determine which one of these it is, then we needed to know the coordinates of these vertices, or if you want, corner points on the shape. So we need to know the coordinates of these vertices. And that information wasn't given to us. What was given to us was the equations of the lines. So here's a long line, here's a line, and I need to find where they intersect. So before we did any math, we decided that we needed to kind of get a feel for what this system looked like as a whole, so that we knew which lines intersected and we had a sense of what was happening. So we used this graphing software called Graphmatica, and we had it graph our lines, and we labeled all these intersection points so they have a name, A, B, C, and D. And then we kind of said, well, we know it's a parallelogram, and boy, that sure definitely looks like a parallelogram. And it definitely doesn't look like a rhombus, but we have to make sure of that. And again, the way to make sure that it is a parallelogram, but not a rhombus. So we know it's a parallelogram, but we don't yet know for sure if it's a rhombus or not. We're going to look at the length of side AB and the length of side AD. And if these are not the same length, then we don't have to do any more math. We know for sure it can't be a rhombus and therefore it's a parallelogram. And again, the first step to doing that is to find the coordinates of the vertices. So in the last video, I had found the coordinates of point A, and I had said, before watching part 2, take out your pencil, paper, calculator, and you calculate the coordinates of B, C, and D. So hopefully you did that and you got these values. And notice that whenever I have a fraction, the denominator is 3. You definitely, absolutely do not want to be using a decimal because there's no such thing as a perfect decimal. You're always going to be rounding. So that's why we stick to fraction form in academic high school math. So again, I want to find the length of AB and the length of AD, and I want to find out, are they the same length or not? Same length, hey, I have a rhombus. Different length, I have a parallelogram. So how do you find the length of a line? Well, the length of a line is defined as, technically it's the length of a line segment, because a line is infinitesimally long. Um, is that right? Infinitesimally? Or does that mean really tiny? Oh, infinitely long. Yes, there. Okay, a line is infinitely long, so there's no measurable length. It goes on forever. So technically what I'm talking about are line segments. To find the length of a line segment, we use the distance formula, because this formula will tell us the distance from one point to another point. And that will translate for us into the length of the line segment. So let's find the distance between point A and point B. So looking up here, point A and point B. So x2 minus x1 squared plus y2 minus y1 squared. And I should put something over here like I'm finding the length of AB. So isn't it nice we already have common denominators? So denominator 3, 14 take away 4 is 10. Again, denominator 3, 8 minus 13 is negative 5. Okay, keep going. Now I'm going to square each bracket. 10 squared is 100. 9 squared is 9. Negative 15 squared is 225. 3 squared is 9. And now I'm going to add those fractions under the square root. So 100 plus 225. So I have 325, and my common denominator was 9. So again, at this point, this is where, depending on what your teacher wants, you could either just take out your calculator and calculate the decimal version, like whatever this would be in decimal form, or maybe you leave it like this because all we're doing is looking to see if I get the same value. But I'm just going to do the extra super fun math with you just in case, because it's always good to see examples of math that you may be expected to do later on in your math career. So when I'm square rooting a fraction, I can separate that into the square root of the numerator and into the square root of the denominator. And that's kind of nice because I know that the square root of 9 is just 3. Now, 325 is not a perfect square. So we have to do something called reducing a radical or simplifying a root. And how do you do that? So you may have seen this in another video. Let's go through it again. In my brain or on my piece of paper, I keep track of the perfect squares. 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, etc. squared, right? And my job when I'm reducing a radical is to find the biggest one of these that evenly divides into 325. So like, does 325 divide by 4? Or does it divide by 9 and so on? So this is where you take out your calculator, depending on your multiplication skills. You take out your calculator and you just press buttons and you find out 324 divided by 4, 325 divided by 9. And you should discover that 325 divided by 25 is 13. So 25 times 13 is 325. And that means I can rewrite this. Instead of 325, I'm going to write 25 times 13. Now, there are a lot of things I could write. I could write that 325 is 5 times, hang on a second, 65. The problem is that's not useful to me right now. I need one of these to be a perfect square to do this process. So yes, 5 times 65 is 325, but I only care about these green numbers when I'm reducing a radical, and here's why. The square root of 25 times 13, again, because it's multiply, I can separate that into square root of 25 times the square root of 13. And why is that so good? Well, because what's the square root of 25? It's 5. So I really have 5 times root 13 times 3. Now, you may not think that that's a simplified version, but mathematically it is. That is mathematically a full simplification of square root 325. And again, that's the length of AB. So now we have to find the length of AD and see if we get the same value, yay, rhombus, or a different value, yay, parallelogram. So let's go to the next page. And again, we want to find the length of A and D. So again, the length formula involves square rooting. So square root of x2 minus x1 squared plus y2 minus y1, oops, squared. So we need to get common denominators. Oops, that was a strange looking line. This time we need to get common denominators. So instead of negative 6, I'm going to say negative 18 over 3 minus 4 over 3. And again, instead of negative 3, I'm going to say negative 9 over 3 minus 13 over 3. And let's see what we get. So denominator is 3, Negative 18 minus 4 is negative 22. And that's going to be squared. Denominator 3. Negative 9 minus 13 is also negative 22. So let's see. Now I'm going to square 22. What's 22 times 22? 484. 3 squared is 9. I didn't need a calculator for that one. So 484 over 9. You know that a negative times a negative is a positive, right? Of course you do. Of course. So 484 plus 44 is 968 divided by 9. So I already know that that is not the same length as AB. But since we have a little bit of time in this video, let's actually practice that process we just did. Let's reduce this radical and simplify fully. So again, separate the top and the bottom into separate radicals. And we know that the square root of 9, we know that the square root of 9 is just 3. 3. So let's deal with 968. That's a weird one. 968. So, oh boy. 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. I want the biggest one possible. So, let's see what happens. Let's try. And again, just like you, I'm sitting here in front of a calculator and I'm trying different numbers. 36 didn't work. 16 doesn't work. 4 works. I guess that's the best I can do. Yeah, all right, fine. I mean, feels like there might be something bigger, but I guess since it's sort of irrelevant to the question, maybe I'll pause and take a minute and really check for sure. Okay, so you'll notice that there's now an awful lot more perfect squares in my brain bubble here. And I realized as soon as I saw it that I should have known 484 is 22 squared. And I should have known to use 22 squared because when I went back here, I did 22 squared plus 22 squared. So that number should have occurred to me to check anyway. But, oh well. So, 484 times 2 is the same thing as 968. So instead of 968, I write 484 times 2. And then separate it. So 484 square root times the root of 2 over 3. And then the square root of 44 is 22. So there I have my full simplification of the length of side AD. And obviously, we knew this quite a while ago, but you know, we love math. Obviously, that's not the same value as 5 root 13 over 3. And that's one thing. When you fully simplify a radical, then you know for sure whether or not they're the same value. I mean, if I had left this as square root 325 over 9, and if I had left this one as root 968 over 9, yeah, I would have known they were different. But this way I know for sure, because if they don't reduce to the same thing, then they're not the same. So now we know, new page, now we know that the length of AB is not the same as the length of AD. And therefore, this is not a rhombus. So what is it? Opposite sides are the same, are parallel. Both sets of opposite sides are parallel. Side lengths are not the same. Therefore, this is a parallelogram. Oh, I can spell really good. Parallelogram. There you go. It took 2 videos, lots of paper, but it was just good, clean fun. All right, so I hope that helped. Good luck studying. See you in school. Bye-bye. Bye-bye.